Hi everyone, today we're going to be talking about the Productivity 1000 Series PLC data handling instructions. And in our Productivity 1000 software suite, we have 15 different data handling instructions that we can see up here on our screen. And we're just going to cover the first 8 today in this part 1, and next time we'll look at part 2 and cover the remaining 7. So the first thing is we are connected to our PLC through our Ethernet port, and it's right down here. If we actually look at our controller, there is my Ethernet port connected right here to our software package. And the first instruction we have is an absolute encoder, and the absolute encoder it comes in either gray code or binary, and you can select how many bits you have for that encoder itself. In my example, we're going to use gray code, and we'll use 5 bits, which will give us 32 pulses per revolution of that encoder. And absolute encoders are ideal because what will happen is every time power is removed and restored, you know exactly where it is in that rotation. So hit OK. And the actual code itself, we can look at it. So decimal will do the first 8 different points. Then we have binary, and you'll see 0, 0, and gray code is 0. And same with 1, 1, and we have 1 here. When we go to 2 though, you'll notice that binary, 2 digits change, the first 2, where in gray code only 1 digit changes at a time. So that means that as that encoder turns, you can only change 1 bit at a time. So that means that when power is shut off and power is restored, you know exactly where that encoder is, or that rotation is, when the power is restored, because only 1 bit changes, so it can only be here or here. Whereas if the encoder changes here, we have 2 bits changing. So because the 2 bits changing, it could be several, so it could be anything. So binary is more difficult when you're dealing with that kind of encoder to know exactly where that position is. So you'll see here that if we have the value 5, we'll have all first three bits on, and that'll be the value 5. So that's the main difference, is that remember that gray code, only 1 bit changes at a time. For binary, several bits can change. We'll just close that down. And what we'll do is we will actually turn on our switch number 1. So it will encode for us our inputs. And what we'll do is look at the data view. And under the data view, we will put in, edit this, we'll put in a value of 7, which will turn on the first 3 bits, and exactly as expected, our encoded output actually represents 5. So the 7 that we're putting in here, I know it's a binary number, but we're actually just forcing those bits on, and it's the first 3 bits that we're forcing on, it becomes a 5. So that's the absolute encoder value. Now if we look at the next instruction, which is the compare instruction, our compare will basically compare 2 inputs. In this case here, we're using a structure, so we're using compare value as the name of that structure. That automatically sets up our tags. So our tags input 1, input 2, and then we have 3 bits, the greater than, equal to, and less than flag bits. So we'll just hit OK. And once again, we will turn on switch number 2. And when we do, you'll see that currently right now I have my equal flag on. Now let's take a look at the data view, and we can go to the compare, and let's change the second value here to the value, let's go below, so 2000, and we will send that in. And now when we do that, input number 1 is greater than input number 2, so the greater than bit comes on. And if we were to edit this again and put in 3500, and send that to the controller, you'll notice that now we have the less than bit. So input 1 is less than input number 2, so the less than bit flag comes on. So that is our compare values. The next data handling instruction that we'll look at is the copy command. And the copy command, what it will do is take in a source and copy it to the destination. And you can see here I can have several different values here, and it does that all at one time. And we can copy the value or copy binary. So we said OK. And in our particular case, we're going to copy the value of input number 1, which is right here, to input number 2 when we turn on switch number 3. So let's do that. There's switch number 3 just turned on, and you can see now that instead of being 3500 in input number 2, we have 3000 again. So this is copying at every single scan into my destination channel. So that is my copy command. Now the next instruction is a very powerful instruction. It's called the first in, first out, or last in, first out. So it's FIFO or LIFO instruction. And what you'll see is, well, the best way to explain it is an algorithm or an analogy here. And let's take a look at the this analogy. We have an input, and we'll use the input as tennis balls into this sleeve. So what we have is our input, which would be a number, and it's going into the sleeve. So as I put each input in, it continuously drops the next number into the sleeve. So I have a stack of these numbers. Now when I use push, that means that I'm pushing the input into that sleeve. If I use a pop, a LIFO pop output, that means that I'm taking the last one in, and I'm going to take that first one and then take that out. So it's just like it is here. If I take the lid off this and take the first tennis ball out, that'd be my first number that or the last number that I pushed into that that stack of memory. And then if I had the bottom cut out of my sleeve, and I could use the first in, first out. So as I push these numbers into the sleeve and use the pop output, and I'm using a first in, first out, that last tennis ball would come out first. That means the last number that I put in, or the first number I put in, would be the one that comes out of my instruction. And the other thing we can do is we always peek, and we can look at any number given the index reference that we have within our stack of numbers. So that's a quick analogy of how the first in, first out, and last in, first out instruction will work. So let's look at our actual instruction itself. And here we're going to use the structure FIFO LIFO. That will automatically set up our input, which is our push. We'll set out our output, which is a pop. So we push and pop. Then we have a peak. We have an element number here, and copy to where the peak will go to. Our element type is a FIFO, so we're going to take the bottom of that can. So the first number in will be the first number out of the stack of numbers that we're going to look at. And what we'll do is we'll have a buffer size of 100, so we can store 100 of these different numbers in here, and we'll use a one-shot. The one-shot just means that when we have the stack of numbers, it'll only take the first number or it'll do it only once and put it into the instruction itself. So let's hit OK here, and what we'll do is take a look at our data view, and you'll see here that switch number 4 pushes that information onto our stack. So let's look at our LIFO and our input here, and we'll change this number. We'll go 1, 2, 3, 4, and we will write that to our input, which we see here. Now once we turn on switch number 4, you will see now our buffer count is, our element count number is 1 now. So we have 1 on our stack. Let's put another number in. We'll put in 5, 6, 7, 8. And what we'll do is we'll have to turn that switch off again and turn back on. And again, now we have 2 in our stack. And then the last number we'll put in is, we'll say 234. Again, we will toggle that in. So now we have 3 elements in our stack itself, so we have 3 numbers. And what we can do is we can take a look at switch number 5. Let's just close this down for now. Switch number 5 now, it will turn, when it turns on, it will take the first number we put in, which is 1, 2, 3, 4, and it should put to the output here location. So if let's take switch number 5, we'll turn it on. And sure enough, what we see is the output 1, 2, 3, 4. Our element count now decrements to 2. So let's look at the switch number 6. There's a peak. So let's go back to our data view here. And let's look at our element number. Look at 1. We'll write that in. And then when we look at our peak, turn on switch number 6. Okay. Then switch number 6 to our output, you'll see that we have copy 2, which is 5, 6, 7, 8. So that's going to be the next instruction, or the next variable that's going to come out of our FIFO instruction. So that's how the peak actually works. So we'll close this down, and what we'll do is we will hit the pop again. So that should be our next output. So turn that on, and sure enough, our output 5, 6, 7, 8 now appears on our output channel. And we still have 1 element left, which is the last number that we put in, which is 2, 3, 4. So when we do that, now our buffer is empty, and it gives us an indication that our buffer is empty. So FIFO instruction, LIFO instruction, very simple to implement within the Productivity 1000 series controllers. The next instruction is going to be our first bit on-off. And our first bit on-off, what you see here is the structure. It takes a look at our elements up to 8 bits and will determine exactly when the first bit turned on and give you that corresponding bit number and reference. So we'll just hit OK. And the best way to describe this is to actually look at the sample. So we'll cancel that. And let's look at our data view. And we'll go to our first bit on off. And what we'll do is we have this switch number 5 on. So let's look at bit number 3 here, and we'll force that. Okay, so it automatically tells us that the first bit here is number 3. If I turn on bit number 7, and we'll energize that one, again it still stays bit number 3. So then if I turn on bit number 5, force that, again bit number 3 still stays on as our first bit that was on. So let's take bit number 3 and let's turn that off. Right? And what we'll do is then turn switch number 5 off, and then turn switch number 5 back on, and now the first bit is going to be bit number 5 that came on. So it takes the first bit that it sees and turns it on. Now any subsequent bit during that on time is going to ignore it. Now let's turn that one off, and we'll turn 2 on. Alright. And so since we did that, we'll try bit number 5 off again. And again, the first one that sees during that transition from off to on is bit number 2, which is now active. So there are applications out there for this instruction that will help you in your logic. Now let's take a look at the next instruction, which is my increment decrement. So I have my input here, and again we use our structure of increment decrement, which goes back into the tags, and it automatically sets up 2 parameters. We have the amount and we have the output. And we'll use a one shot on our input sides, both the increment and decrement, to control this instruction. So we'll say OK for that. And switch number 6 and switch number 7, 6 will increment the value. So it goes 20, 30, 40, and we've actually incremented by 10 each time. So if we decrement, that would be switch number 7, 30, 20, 10, 0. It will even go negative 10, negative 20. So this could be very helpful when you're, say, counting objects going by or counting batches. Very straightforward and easy instruction to use. Next we have our logic bits. And logic bits allows us to have, there are 2 inputs, and we can use the basic AND, OR, NAND, NOR, or exclusive OR instructions within those 2 bits, or those 2 rungs that are coming into the instruction. So in our case here, we're going to use the logic option NAND, and our output currently right now is 1. And what we can see is that if in an AND instruction, if both outputs are off, it'll be a 1, and when both inputs are on, it'll be a 0, and either input is on, it'll still be a 1. So we can try that out with switch number 7 and 8. We'll turn on 7, still a 1. We'll turn on 8, still a 1. Turn on both of them, and our output now turns to 0, which we see here. And our last one we're going to cover in this part 1 series is our logical words. Now the logical words, what it will do is take 2 words, and in our case here we're going to use logical words as our structure. We have input 1 and input 2. These are words, and then we have an output. And what they will do is do a logical AND in our case here, but we could do an OR, a NAND, a NOR, or exclusive OR on this on these 2 words. So we'll set OK, and in this case here we're using an AND. And what we're doing is we're taking our input 1 and we're ANDing it with the value 255, which is the first 8 bits of the word itself. So basically what we're doing is we want to mask that input and to the output. So the maximum number I can have is 255. So if we look at the data view and look at the logical words, we'll see that here's my input, and let's edit that, and we'll put in the value of 52. Write that, and what you'll see is 52 automatically comes up on the output. Now if we put in the value of 1234 or 1234, we'll write that in, and again the maximum value is only the first 8 bits, which corresponds to 2000 or 210. So that represents the first 8 bits of that word that we're actually putting in. Right, so that is the logical words. So very useful when you're trying to mask information within the controller itself. Now all the links and Documentation can be found on our website at accautomation.ca. And if you like this video and like to see more, there are 3 ways in which you can help us out. You can give us a thumbs up so other people can find this information just as you have. You can subscribe to our YouTube channel. You can also go to ACC Automation and subscribe to our website. When you do, notification will be given to you every time we publish new content to the site. You'll also get 2 free ebooks on numbering systems and robust data logging. And the third thing to do to help us out is tell a friend or colleague about the site. Alright, that's it for now. Thanks for watching.